Hi class, in this lab, we will do acid-base titration. So let's look at what is the acid. Well, you can see we talk about the acid base. There are three levels of theory about the acids and the base and the bases. So let's look at the acid. So the very simple definition about the acids is shown here. Acids can produce a proton in water. So this one is arenous. So let's write that arenous. Arenous acid base, but this is the oldest definition about the acid base. Basically, produce proton in water. Then after that, there's a Lowry, Lowry acid base theory. It means the acid is a proton donor. Then the base is a proton acceptor. So this is the base. This one is the acid. And for here, this one is to produce proton. And another one, base, will produce hydroxide. So this mostly cases applied for aqueous solution. And this one can apply for more general, even in non-aqueous solution. Then a larger, broader definition about the acid base will be Lewis acid base. In this case, acid base will be, so acid will be electron acceptor, electron pair acceptor. Then base will be electron pair donor. Well, this one is easily understandable. So you can see proton has vacant orbital. There's no electron, so they will accept the electron pair. So that's how you say electron pair acceptor. That's an acid. So anyway, let's see this one. So we will keep that the simplest definition about the acid here. So hydrochloric acid, this one's a strong acid. So for the nitric acid, and in general, for a strong acid, the way we call that as a strong acid, it's basically in water. This one can fully dissociate. Fully dissociate. So that's how, once you put this acid in water, this one does not exist anymore. Because that's a fully, completely changed to proton or dissociated proton, and this case we call conjugate base. Right? So, and here you see this one, we most cases write as a hydronium. So in this case, because the free proton will be in combined with water. So because here is the vacant orbital and the water has a non-pair electron, this can combine with that. So that's form hydronium ion, right? Those are the acids. Likewise, for the bases, we say that similar to the definition of acids, this case base will produce hydroxide in water. So sodium hydroxide, a strong base. So for potassium hydroxide also. So in general, the strong base also should be dissociated completely. So that means you put this one in water, this one does not exist in water anymore, because that fully dissociates to those two species, right? Only when you remove the water, they can recombine to form that one. So that's a strong base. Now let's look at the reaction between strong acid and strong base. Say what happened, what actually behind what we see. Normally, if you see this one here, we call, since here's only one proton, we call monoprotic acid. Monoprotic acid, right? So that means there's only one proton. And it reacts with this base. You will form a water, and this one is a salt, the overall salt, right? So we can generate the another equation like this: acid and the base react to form the water and the salt. So that's general. Now let's look at what actually happened. We know if you have a solution of acid, since this one strong acid. So here we mentioned this one actually not exist. So actually you only have a proton or hydrogen ions and plus the conjugated base. And for this base, actually you have a cation associated with water and hydroxide. So actually, but if you put them together, the actual reaction sounds like for here, it's not correct now. It's actually changed to, so we will have changed to, you see, to this equation. So then you can do for this, like this one, you have plus go to water. This is the late ionic reaction, right? So when you do acid-base titration, you actually carry out this reaction because all the thing we see here, metal cation, they actually stay, you see on the both sides stay the same. Even for those conjugated bases, they stay the same, they can be canceled out, right? So the only thing left is this one highlighted here in the yellow color. You can see those are the left, right? So let's look at the what is titration. Titration is the analytical methods that's used to determine the concentration of acid or base. So it depends which one you want to find out. By reacting it with the base or acid of known concentration. That means say if you have an acid and you have a base. For anyone, so one of them, the concentration is known. For example, this one concentration is known. Then you can apply this, allow them to react to find the concentration of this one according to the titration. So this one, during the titration, you will find the equivalence point. This means their reaction completely. So this case, right? How to measure the equivalence point? Then we can either use pH meter. So pH meter basically, since this one's pH meter and a meter, that means to measure something, the tool to measure. So this used to measure the pH. So this case, you can actually construct a graph of pH versus the volume of titrant you added to that to find the equivalence point. We will see this later on. Another one use the indicator. And this indicator require this indicator or form. Indicator basically are the weak acid or weak base mostly, and they will change color at the endpoint. Okay, so let's see what are the pH meter and what are the indicator. So this one is we use the pH meter. So for this case, so what's the pH? You see, we talk about a pH versus the volume. So we talk about pH meter, right? So what is pH? pH actually is a concentration scale. pH actually is a concentration. So how you can see pH by definition, pH equal to negative logarithm of proton concentration. So this one, we know this one actually is the concentration, right? In molarity, how many moles? But we take a logarithm scales, let's still show the concentration, but at different scale. So the pH still is a concentration scale. So in this case, we can apply the pH meter to monitor. So for example, at the beginning, you have you don't have a volume of the base added, for example, as non. So this case, you will be very acidic. We know pH. Notice that pH equal to 7. That means the proton concentration. We take an analog, right, equal to this one molar. And so this, since this was a negative log, so the smaller pH, right? Then more acidic. Likewise, the larger the pH, then more basic, right? So in aqueous solutions, we know in aqueous solutions, so in aqueous solution, since that's in aqueous solution, in let's say neutral, pH equal to pOH, right? So, and this the scale of the pH is starting from 0 to 14. So you can see the middle point will be 7. So you average them, that will be 7. So that's how we say find out this case. So this only apply for the titration of using the strong acid with the strong base. So this time you can use a pH meter to measure the change of pH as you add the base to the solution. You see, without that, so this one no acid, no base added, this will be very acidic. As long as you add the base, the pH will, because you add the base, the solution gradually change into more basic. So the pH will rise, right, slowly until they reach the end point. This case here will be dramatic change. After that, they will go slowly. So in this case, we can construct the titration curve and find out where that one is the end point. And this way we can find the volume according to how much volume we use. Remember that the principle behind those titration is actually to find the volume, how much you used. If this is the volume, right? And we know the molarity of or concentration of one solution. For example, base, you already know. So base concentration, you know. We know volume multiplied molarity, that give you number of moles, right? And since they react equivalently, so you know this mole, you can allow this equal to moles of the acid. If this equal to mole of acid, and how much acid you already know using the NMR flask. So how much acid you try to titrate. So this amount you know. So the volume you know. So from that, you can divide that to find out the concentration of acid, or vice versa. You can find out the concentration of base, depending which one you are known, which ones are unknown. So that's the principle for the titration, right? Now, then we will, if you don't have a pH meter, right, we can apply indicator. Indicator, so this one is a weak acid or weak base. So this will have a color change when the concentration of those proton or hydronium or the hydroxide change. So if you apply a weak acid as indicator, so this one's weak acid. Now, this one will dissociate. Let's say here, we will not use equal, we use the form the equilibrium, those symbols. So that means they only dissociate partially here. We will say partially. So that means they have both this one and this one. And those two, because one has an ionic state, show the negative charge, another one neutral, those two will show dramatic contrast of color. So you can see this equilibrium as go start, right? So when this start, remember those are the weak acid, weak base. If you try to titrate a strong acid, strong base, for example, you will titrate a hydrochloric acid with base with sodium hydroxide. By the same time, you add this weaker acid as indicator inside. So your solution contains both strong acid and the weaker acid of the indicator. Now the question is, so this is strong acid, so the strong acid will react with sodium hydroxide first. Only when the strong acid is run out, that will be reach the equivalent point, then the additional base added will react with this indicator and convert that to this one. So you will see color change. So that's how for the indicator, we only need a small amount, just but that one can give us very sharp color change. That's the principle for using the indicator, right? So anyway, we mentioned that this one is high, so pH is low. So equilibrium will be if you have this one, the pH is low, you have more protons. So this one's more proton. Let's see this again. So at the case of acidic, so pH is low, and you have a high, this one high, according to this equilibrium, you can see what shift the equilibrium goes this side. So actually you will basically see the color of this one. But when you have the pH low, so here, when this proton concentration is low, pH is high. So let's see this case. And this one is very low now. And you will shift the equilibrium goes this side. So that's how you're more likely to see the color of this one. That's how we can use the indicator to tell where that equilibrium stays, right? Now, for this case, we can have phenolphthalein. So this is the one is a weak diprotic acid indicator. You can see this one has two protons. They can give out two protons at different levels. So the structure shown here. Notice that here is one proton, and where's another one? You can see that where's another one, this one, right? So this one will show colorless. You can see colorless because this one are the small conjugated system. So that will show colorless. You can see that. However, if you add them a base, the base will deprotonate this one. They will allow this one to go here. Then you can see this will form a large conjugated system will show this pink color. So easily see that a pH change about 8.2. Now notice that this one pH change at 8.2, and for the strong acid-base titration, in the point is close to 7, right? So you can see that 8.2 is very close to 7. That's how we can use this one as an indicator. Now, in this one, we will do the titration example. Say you want titration of 10 milliliter of hydrochloric acid and unknown concentration. So the concentration we don't know. And require, so you actually measure 12.54 ml of 0.1 molar of sodium hydroxide. Then we will ask what's the concentration of hydrochloric acid. In this case, you can see it's stoichiometric ratio of factors 1 and 1. So we will know that at the equivalence point, the moles of hydroxide equal to moles of protons, right? So in this case, moles of the hydroxide, according to that, is the molarity multiplied by the volume, and we have the molarities here, 0.1, and the volume is this one, but this one we have to change it to liter, right? So we divide it by 1,000 milliliter. So this is the converting factor. So we will find out how many moles of this one. And you can look at that. This one's a 3 significant number, and this one's 4. So after that, since this is a multiplication, so we can only keep 3. So after that, we have to drop this one. So we have a 3 significant number, right? So this is the moles. And this moles, because here we say the moles of a proton equal to moles of hydroxide. So we can simply think about moles of protons or the same amount. And this one, we know the volume we use that is here. So we can use this one divided by that. That's how we find out concentration of hydrochloric acid, right? Now, this one here, titration of a measured volume of hydrochloric acid unknown with this one. So you can do two methods for this map. One method A is we use one drop of those indicator, right? So you can add the sodium hydroxide in increment. So for example, you have a, so let's say titration. Let me see, titration, you need a stand. So here, let's see, you have a stand, right? And this one have the trap to hold your burette. And the burette have a very nice scale about the volume. So this one and the bottom, you can strip them, the titrate. And the bottom, you have an enamel flask. This one will hold, so for example, this one's a hydrochloric acid we fill in, and we don't know the concentration of that. But the bottom, we can fill that. So, okay, here, let's do this one. This one we fill with sodium hydroxide, which we know the concentration. And the bottom is hydrochloric acid. We don't know, so HCl, and we don't know the concentration, but the volume, no. How do we know that you certain how much you transfer to here or how much you measure here? Use the transfer pi. So you can transfer either 15 or 20, 25. Normally we keep them at 25 because a small amount sometimes is not accurate. So we will use a 25. So in this case, if you have a one drop less, so you have less error. So normally we use 25 milliliters in here. So the volume is low, but the concentration we don't know. Then by the same time, we add the indicator to that. So this one will be colorless, right? Because this is the acid, colorless. Then you can add it, this base. And base concentration, you know, you just drop them from at the beginning, you can have an increment about 0.25 to 0.5 milliliter a time, right? You can drop to there. Now, as you see, so near the end point, you can see when we know that. So if you have a solution like this one, you have one drop, you immediately see the color change, then the color gradually fade. So this will tell you it's close to the end point. Then you need to slow down that. So you can see, add this drop by drop. Every drop you mix and shake this one and see the color stay. If the color stay normally, so you can see we will look at the color stay roughly about 5 seconds, minimum 5 seconds. You don't see the color fade, then that tells that's in the point, right? And here you see burette can be rated to nearest 0.01 milliliters. So this one you will have keep these decimals. All the volume you recorded from this experiment, you have to keep these two decimals here because the burette actually have the two scales. So one is larger scales, and so there's something like this, and then there's the smaller scales. So for example, then you can rate them for the larger, then you have an estimate. We normally estimate that from the minuscule of the liquid levels, like this one, to rate the volume. So you need to practice that. So after that, you need to repeat the titration. We ask you at least once. Typically for the analytical lab, we ask them at least repeat twice. So you have three values. In that case, you have 3, 1, 2, 3. And in case one is outliers, you can easily average the other two, see which two are more consistent with each other. So this is the way you can use the indicator. Another way you can do that is using the pH meter, right? pH meter. So pH meter works this way. Again, you have the stand, for example, right? So you have the stand, then we hold the burette, right? Burette has the scales, and so this is still base, and the bottom is still your NMR flask. In this case, since you use a pH meter, pH meter is you have a probe. So probe should always be inserted into the liquid level, and this connected to a meter. Right? So this meter will be able to read the pH values. So you add them to here, then the pH change, you record them. Then, so you see that you can see how much increment of base you added here by the change of pH about 0.2 units. But in this one, in this range, you need to add sodium hydroxide drop by drop, right? Until, so remember this titration curve go here. This the range goes so fast, but after that it will go slow. Only go here, that's guarantee your this endpoint is achieved, right? So after that, you normally titration use pH meter. We ask you to titrate until the pH go to 11. So go to 11. In this case, you can create or construct a complete range of the titration curve for this one, right? So then you make those So you can record every moment you add how much base you will rate them, how much base you add, then you rate the pH. Then, so after that, you should be able to collect a table, something like this. Example here, right? You use this one of their sodium hydroxide, and here this will be the volume, like a right volume. So initial pH is here. The volume you add that, everyone you add that, and that's the actual pH you recorded that. So you are according to that, say this is the pH versus the volume, you will be able to create this titration curve, right? So from here, you can easily find the endpoint and cross here, you find the volume, and according to the volume, you will be able to find those molarity of hydrochloric acid. So something like this, you will be able to do. So this lab, you can use both. One use the indicator, another one use pH meter, right?